Hello, everyone. Thank you for your patience and apologies for the delay. Welcome to GraphReader Agentic RAG, Rethinking Long Context Retrieval Systems. Today presenting will be Jayita Bhattacharya and Soumya Ranjandas. Soumya is going to be joining us shortly, but I'll hand it over to Jayita to take it away.
Alrighty, are we good to go? Okay. Hey everyone, thank you for joining in, and we're going to discuss about a very interesting topic today called GraphReader Agentic RAG Rethinking Long Context Retrieval Systems. So this is a research paper implementation with the same name GraphReader that came out around last year November by some of the researchers at Alibaba Group and other institutes. And so our take is a bit different from what has been discussed in the paper. There they have used closed source models, so we tried to reproduce the same using open source models and tools, and also we tried to implement on top of what has already been done, and we'll be discussing all of those today. So let's get rolling, and we'll be basically trying to cover what traditional RAG challenges are and how GraphReader helps you overcome that. And GraphReader is basically GraphRag plus agents, and we'll see how you can construct one and go through the traversal and retrieval process. And what's better than showing you a live demo that we have implemented. So on that note, let's try to address what are the problems that you face while building search and retrieval systems. Most of us have already, I'm sure, been working with some kind or the other with the RAG systems, and when you implement a naive RAG, you cannot expect to get the best of answers from your knowledge base. So essentially, these are the broad problems that we have identified when you go on to implement RAG systems. First is the context window limitations that most of the LLMs have, and it also is the matter that even if with long context windows like 2 million token lengths, there is a problem of lost in the middle or needle in the haystack problem. So these have been overcome by some way or the other, like KV caching and pretty other methods of RAG that you can implement, like the adaptive RAG or the corrective RAG methods. And agentic ways have also been implemented to overcome this. Maybe you badge your processes. Then the next one that comes into picture is the state and persistent issues. So LLMs do not have the memory of their own, but when you are building such RAG systems, you need to maintain certain kind of temporary memory, which will help you process through the next steps onto the actions that you need to next take in your pipeline. So these also have been overcome in some ways. There are memory layers that you can append, and even these agentic architectures, they have a memory built into it. The third problem is when you implement knowledge graphs, there is a big gap when you need to build an ontology or the schema. So without proper SMEs or architects, this is a big problem for developers to build it. So these are the mainly challenges that we identified are causing a hindrance onto when we implement RAG. So we say that enter GraphReader, which is a graph-based agentic system designed to supercharge your long context windows, both in ingestion as well as retrieval. So what GraphReader, the paper proposes us to is that instead of having to read documents linearly, what you can do is you can reconstruct a graph of atomic facts and relationships, then use an intelligent agent to explore the graph in a goal-directed way. So we'll demystify all of this that the definition says. And I call GraphReader a healer because it has overcome challenges in every step of RAG that we do, starting from chunking to retrieval to reflection to context window and multi-hop reasoning as well. So the way that GraphReader works is that it first constructs your graph. The input document is broken down into chunks, and it has the identified key entities, facts, their relationships, and extract it in a form of a graph. And then you go forward with planning and exploration, where you can, when given a question, the agent tries to create a plan. It decides where to start, what to read, and how to proceed. It uses a predefined tool to read read the nodes, its contents, as well as its neighbors. And then comes the shallow retrieve, the context course to find reasoning as well. It begins with summaries, or and then tries to drill down to the end node, and then try to optimize your token usage as well. There is a reflection and note taking. So in you can think of it as a scratch pad that the agent maintains on updating the action plan it needs to take at every step with the learnings that it is doing, and that is an iterative process that it continues. And finally, of course, you have the LLM to synthesize all of these knowledge that it gathered to give you the information. So this is how the paper had proposed. Like it first takes in the document, splits it into chunks. In the paper, they have maintained a paragraph structure while chunking. However, this is a bit hard when you do it in your generic way. Therefore, we can use chunking suitable to your use case. The next step is each chunk is processed by the LLM to identify atomic facts, which are smallest in indivisible units of information that capture core details. So suppose I say a sentence that Joita works for Deloitte and is here to give a session with Soumya. An atomic fact could be broken down into something like Joita works at Deloitte and Joita is giving a session with Soumya. Each atomic fact is focused on one clear standalone piece of information. For these atomic facts and key elements are identified. For the first fact, the key element could be Deloitte and Joita. For the second, it could be Joita, today, session, and Soumya. These key elements are essentially proper nouns that capture the core meaning of the atomic fact that you have in your information. This is a rough prompt that was proposed in the paper, that you define what your key elements, atomic facts are. You say certain kinds of requirements that you have that do not exceed so and so token limit and other essential facts. And you also give it some examples so that the LLM is able to reference it better. During the graph exploration, this is the process that it formulates. I'm not going to deep dive into it because we have implemented a different, we have taken inspiration but developed on top of it. So I'll hand over to my co-presenter Soumya to discuss further. Soumya, are you able to share your screen, or do you want me to continue? Okay, let me share my VS Code. Is my screen visible? Okay, probably I'm not sure why VS Code is not shut up. We try resharing. I hope it is visible now. Okay. So we tried to implement it using Neo4j and LangGraph, which is a very popularly known agentic library that you can use of. And along with that, we installed all the necessary open source other suitable libraries that we will be needing, like sentence transformers for embedding and Pydantic for getting structured outputs, and then of course light LLM, so that we can switch between the LLMs that we wish to. And then we go forward with the function to just get the embeddings out of it. So whenever you have any kind of document that you want to ingest. So just for reference, we are using a very simple PDF document to which is a finance which explains finance terminologies. So it's a very basic document. For sake of simplicity and POC purpose, we try to just show you what is possible. So we define our embedding function here. Then we go ahead and define the LLM that we want to use. I say we are GPU poor people, so we resort to Grok to provide us the LLM, and that the one that we are using is Llama 3.370 billion model. And then we have connected it to our Neo4j instance that will have the data once we upload it. And then we can go ahead and define what our atomic facts is. So this is a class where we define our atomic facts. So essentially, if you saw what I previously shared, that atomic facts would be the nouns, verbs, and essentially any real world entity that you have. And that is the key element. And the atomic fact would be any single indivisible fact as a concise sentence. So anything that is related to those entities will come as an atomic fact. And then we consider that our document is of a unstructured nature, and then we go ahead and write how you can extract chunks. So we basically are doing a chunk extraction here. So once you are ready to ingest your document, so you basically just say where from your chunking would be done. You just write how you just give the input to your ingesting file that you have. And then we went forward with a section wise chunking, which is similar to what has been discussed in the paper, like a paragraph chunking. And then we see how the we leave it up to the LLM based on the prompt that we had previously given to extract the key atomic facts and chunks, key elements for us. And we then create our index, which would save these chunks after converting it to embeddings. And then it will be available to the it will be available into the Neo4j instance that you have. So for testing purpose, we just gave it these 4 to 5 line sentence to see how it works, and it was able to ingest it up. So maybe I can show you that how it looks like after ingestion. Okay. All right. Okay, maybe I need to reshare it again. Let me do a full share. All right. Okay. So this is my RDB instance where my data has been ingested, and it has certain nodes of entity nodes. If you hover over, you will see that it has identified Tesla as a node and $25.717 billion, and so on and so forth as the entity nodes. And if you want to do has entity, these are the relationships that will be captured within the nodes. And this is just to show you how you can visualize, and like there are other options. If you want to see the attached facts that are there to the particular document, then you can traverse more to the graph. All right, let's head back to our VS Code. All right, now that we have already ingested our system, we have already ingested, and if you see here also, we tried to test it out and see what exactly our atomic facts are. It also gives us here that what exact atomic facts it has returned. So now we are good to go with the retrieval step. So this is where we install some more packages like Neo4j GraphRag and LangChain Light LLM, uh, and obviously LangGraph for having the agentic nature. We also keep LangGraph checkpoint sequence so that within the intermediate steps you are able to store the memory that the agent requires to take the next steps. So we import our libraries here. Again, we define the sentence transformers, and then we can go ahead and obviously connect to our ORDB instance, define our LLM here, and then we try to get to our index, and then we define some utility functions here that. So this is basically just to connect, and if the connection just fails, what do you do next? So here it returned a successful connection, and you have both indexes like fact embeddings and section embeddings. So in your retrieval class, you can basically define what are the things that you will be needing. You can you would first have the user query, and it sometimes can happen that the user query is modified to basically a query rewriting happens, which is more suitable for the agent to go up and search for it. And what are the current nodes or the facts that are extracted from that user query? You would have a notebook or the sketchpad per se, which the agent maintains on the steps it has to implement, and you have a traversal count and traversal limit so that you won't be missing out. You won't run into the problems because of like agentic systems have to make the agentic system reliable. And then you go on with the LangGraph agent nodes, where you first so we first implemented using vector retrieval, which uses the vector embeddings and the full text embeddings as well. Later on, we have combined both of them to get the best of both worlds. We combine the vector embeddings plus the so the idea here is first it searches the embeddings, the fact embeddings index to get the exact matches or similar matches. If it does not find it there, it then comes to the section embeddings. So hopefully it finds some facts here. If it does not even find it there, then we are sure that in the full text index it will surely find the match, and that's a kind of full text index will work out there. And then you go to your hop analyzer, which would now traverse the neighboring nodes. So once you have the had the entity extracted, the next thing that you can do is you go on to the neighboring nodes so that they have related information which is more suitable for your graph traversal. So you then extract the neighboring nodes, and then you get information out of it. So we also implemented a context manager here, which basically maintains the so that this is a fallback mechanism so that your LLM doesn't run out of context window. And then you have we also have an evaluate answer. So it can be we have to have an evaluator. So we implemented a LLM as a judge here so that it basically checks three things. First is whether at this stage, after it has hopped to my exact entity and the neighbors, it has the complete information that it needs to present to the user based on the user query. If it is complete, then this will proceed to the LLM to give you out the final answer. If not, it will hop more. So it will go on to more neighboring nodes and more related entities or atomic facts to extract more information, to get related information. And if there is a third step as well, so deep dive. So say per se, you whatever information it got, it is not completely relevant to the user query. So you might have to again go back to a new node and traverse from there. So these are the three kinds of choices that you can make, and then you go to the LLM to decide finally. There is another fallback that can happen here is that it doesn't get any information at all, and then you basically have to. This is like the edge case where even with the deep dive, you have to the notebook or the scratchpad that the agent maintains basically comes up with a retry mechanism, and you have to plan up again that whatever my system has so far extracted is not correct, and I need to again do a query modification there. So all of this happens, and then finally you're able to come up with an answer, so which basically calls an LLM. It gives these things to the LLM, to the original question that was asked, the facts, and the actual scratchpad that it was maintaining to get you the answer. And yeah, so maybe whatever so far I was talking about can be very well visualized from here. So you start, you do a initial discovery, you do your hop analyzer, you maintain a context manager which tries to keep your LLM context window limited, and you evaluate the three conditions that whether it is sufficient or you need to hop more or you need to deep dive. So if it is sufficient, it will get you the final answer. If it is not, it will hop more to the neighboring nodes. And if you need to deep dive, you need to again create a new plan, which is again, you start with the initial discovery stage. So this is what we asked, that what was Tesla's revenue in Q4, and this is what it basically gave us, that it went for a traversal count of 0 and a traversal limit of 3, and it had hit these vector hits. So there were three conditions, if you remember, we discussed that. First one was either it gets the embeddings or it gets the full text index, and luckily either the fact embeddings or the section embeddings or the full text. So it has very well got the match at the vector embeddings as, in the first place, and these were the current nodes that it explored, and this is the final answer that it produced. So this is basically the entire flow that we had in mind to implement, and unfortunately, Soumya is not able to share, or he's having some technical issues. We did some more some next steps as well to this. It would have been great if he could come, but we have linked everything. We'll be sharing the slides and this whole notebook for your reference, and you can go through that as well. All right, let me get back to my slides now. And as we are running short of time, we need to wrap up. Okay. All right, not this one. Okay. So certain things that we wish to cover is that there are certain limitations to the implementation we did. Oh, okay. Sorry about that. So we have not considered compute challenges that you can maybe run into. So when you are implementing into production, there will be large amount of data, and you will need more time to in the ingestion process as well as the retrieval process. It will be something that consumes greater compute. You can maybe think of some optimization techniques that we are trying to currently come up with. So if you remember, in the extraction phase, we were going during the retrieval phase, we were going into three types of indexes. So if possible, we can do that in parallel as well, and then give a weighted average and have the fusion of it to answer at the final. This can be one step. And another thing that we can run into is the non-deterministic nature of LLMs is a problem, where you might miss out on certain information because you are leaving the LLM to construct the entire schema for you, entire ontology for you. So these minor problems can be that it sometimes misses out on the broader information that you really want to do. Another thing that we are trying to implement is undirected or so basically here the path that we took was a kind of directed one. So we are instructing the LLM on how to think, on which nodes to go. Can we do it in an undirected way, so that it is up to the judgment of the agent that where it needs to go and how it needs to traverse, and dynamically it comes up with a more better solution there. So these are kind of some more things that we are exploring, and feel free. So it's all open sourced. We have linked our so you can maybe scan this to get access to our slides, and this is the code repository that we have. And feel free to maybe make a contribution or help us with suggestions on what your take on it is. And we this is a original paper that we followed, GraphReader paper. And there is an excellent blog as well by Thomas Botanic. He's from Neo4j. He has written a very excellent blog on how he has implemented it. So do keep exploring, and help us with your suggestions and anything that you have. Thank you for your time, for hearing us out. And if there is time, we can take some questions, or reach us on socials to bug us with questions. All right. Are there any questions? I see we have 3 minutes left. Let me go through the comments. Okay, let me paste the link as well for anyone who wants to go through, can just refer to this. And maybe I can put down our socials as well, for my social as well as Soumya's social, so you can reach out to us at any point and ask us questions or give us suggestions on what you think could be done next.